Okay, so last lecture, which was yesterday, it was just, a continuation for the rectification application of diodes. So today we're gonna continue that. But before that, let's recap what we have taken so far, or the point that we reached. So we have the half-wave rectifier with a capacitor filter at the output. So this black here is actually the previous output of the half-wave rectifier, just to, domes like this. And we only pass half of the input signal. If it's, for example, sinusoidal signal, we will pass the positive half of this sinusoidal signal. Then we added the capacitor. The capacitor, charges, then discharges until it reaches that point here. Okay, so it will recharge again and then redischarge and so on and so forth. Okay, and we say that there is, some ripple here, ripples, and this voltage is called variable peak to peak, and this variable peak to peak in case of half-wave rectifier is equal to Vmax minus 0.7, this point, which is V output maximum, over RCF, or R load in that case, for example. And this is the capacitance of the capacitor, and F is the frequency of the input, which is 1 over T. And we did the same for the full-wave rectifier, bridge, full-wave rectifier. We had also a capacitor parallel to the output. And if the black here is the previous output without a capacitor, then the red signal here, or the red output, is our output with in that circuit full-wave rectifier. And if you want to compare it to the half wave, you can just draw on exactly the same plot, that for half wave rectifier the output will continue. It will not, the capacitor will not recharge at that point. It will continue until another point which is lower, so the ripple is bigger. That's very, very simple comparison between them. If you want to go analytically and calculate the variable peak to peak, so variable peak to peak in that case is equal to Vmax minus 1.4, which is that point, or that point, any maximum, the output maximum, over 2 RCF. So the ripple here, the ripple voltage is less than the half-wave rectifier case, and that's good. We actually want it to be 0. Okay. Good. So let's continue and modify more our output, our rectifier circuits. If you want to just make this ripple disappears, there is still another an extended solution, we can say. Okay, so if we go to the first slide here, yeah, which is adding a Zener. So we have the half-wave rectifier without just a load and a diode, and the output will be this black signal passing half of the wave, rejecting the other negative half. Then we added the capacitor, and the output becomes this green signal, and we have the ripples. Now, what's gonna happen if we added a Zener? A Zener and also this series resistor. It's important. This series resistor is important. I am not gonna go into the very details of this circuit, because it's really difficult to analyze it, step by step. But we're gonna give a highlight of how to understand the output of that signal. Okay. So basically, if VO minimum, this is previous, output without a Zener, is greater than V breakdown of the Zener, and as you see here, the Zener, so when the capacitor have a charge, it has a positive polarity on that terminal and negative polarity on that terminal. So the Zener here, in regard to the VO, is reversed. And if VO minimum is larger than or greater than the breakdown voltage of the Zener might turn, or probably not might. There are still some, conditions, but let's, give a highlight review of it. Probably turn on in reverse, or breakdown, you can say. And once the Zener is in breakdown, the voltage here, VO, will be equal to V breakdown of that Zener, which is constant. So if we revise or review the characteristics of the Zener, VD, ID of the Zener, so it was something like this. Here is 0.7, and here is the V breakdown. In that region here, if we are in breakdown, the voltage will be positive, negative in that, and equal to minus VBD. Remember here, the Zener is connected in that way. So if the voltage in that direction equal to minus VBD, so in that direction would be equal to positive VBD, which is the V output. So we can say that the voltage of the diode will be, the output will be something like this, the steady state output. So let's say what's happening before that, we just ignore. It's transient. It's a transient state. And this is the steady state output, equal to this value here is V breakdown of the Zener. Okay. That's not a very perfect solution, because as you see here, we reduced the sum of the power. So the input power is actually the input power is something like this. That's the input. But let's assume our input now, is the voltage at the capacitor. So the previous voltage without a Zener, it was this green signal. So we just cut off, we can say, or clip it at V breakdown. So all that portion here, let's draw it, yeah. All that portion is lost, by the way. And that's not good. But on the positive side, we get some very steady state or very constant or DC, okay, at the output. But we lost some power, that's for sure. Okay, if your application is really, sensitive to the DC value and really needs the DC value, for example, if the load is a speaker, speakers usually sensitive to the input signal. So if you want a DC voltage at this for this speaker, then you should use something like this Zener, and of course you will lose some power. That's not very efficient, because if it's a speaker and you left the input, the output, like the one with the ripples, the green one, this green signal here, then you will hear some humming, some very small noise come out of your speaker. And if the ripple is big, this noise will be higher. If the input is a perfect DC to the speaker, you will not hear such noise. So it depends on the applications that you have. If the application is tolerable to some variation in its DC input, then don't use the Zener. Just use the capacitor, and that's very good. If it's sensitive like a speaker, no, you should use a Zener at that time. Okay, now just one last important information is about this R. So here, what is, if we look at this, if this is an ideal, straight line like this, remember that the slope of that curve, this dotted curve here, is delta I over delta V. Ideally, this is equal to infinity. The slope here is infinity. So the breakdown resistance is the equivalent breakdown resistance of the Zener is equal to delta I over delta V VD minus 1 is equal to 0, ideally. So based on that, if the output is something, if we neglect this R and just connect the Zener directly, like this, can anybody imagine what's gonna happen if we just, if there is no R here? Any thought?
Sorry, you want to say that again?
So in the original circuit here, there is a series resistance between the capacitor and the Zener. If we just shorted this resistance, if we just put the Zener directly and connect the Zener directly to the capacitor, can you imagine what's gonna happen if we do that? Knowing that the breakdown resistance of the Zener is almost zero, very small.
The capacitor never charges past V breakdown, and so past that point in time in the waveform, the voltage decreases, so it's never going to be above it.
And even the capacitor charges, okay? So when the capacitor discharge, it will see in front of it, a short circuit, just like this. Short. as if there is no Zener or R load completely. And if you have something like this, then in the beginning we have, I'm sorry, it's bad, but anyway, in the beginning we without a Zener we have, you know, this charge rate like this. With a short circuit, it will become something like this. So you didn't do anything. It returns back to its, you know, to its original state when as a half wave without any capacitor or any Zener or whatever. Okay. So this resistor here, if you add a resistor here, so let's do it again. So even if when the diode operates in reverse bias Zener and become, you know, short circuit like this, you still have this resistance. Okay. So tau now approximately equal to RC, not RLC. Exactly, it should be equal to R plus R breakdown of the Zener parallel to RL. But since R breakdown of Zener is almost zero, it's very small. You remember, guys, when you measure the forward resistance of the diode, okay, in that region here, it was around 0.2 ohms. I think this was lab 3 or lab 2, I can't remember, or 3. Okay, one of these two labs. It was very small, almost zero. And of course, in parallel, the smallest resistance dominates over the a parallel combination. Okay, guys, is this clear? So here tau, let's write this, tau, which is very important during this charging, is equal to approximately CR, not CRL. If we wanna, you know, just write it exactly, it's a C multiplied by or times R plus RL parallel to R breakdown of the Zener. Since R breakdown of the Zener is very, very, very small, so this thing here will be approximately equal. It's actually less than R breakdown. Okay, and R plus R breakdown is approximately equal to R. If R is big, even 100 ohm will be sufficient to be, you know, much larger than or much greater than R breakdown. Okay. The only, you know, the only part that is really annoying, maybe this part. So you just ignore it. Okay, we'll see in the lab. We are not basically you will see only the steady state. You will not see the transient state. Okay. Okay, guys. So the good thing about this solution is that you get, it's not perfect, by the way, but you know, much better than the previous output with the ripple. If you wanna, you know, some perfect DC, we can say. But the downside is that you clip, or you know, you cut off the previous, which is the ripples, at a point smaller than V output minimum of the ripple, this point. So you lose all that power. All that power is lost. This is downside. So let's write those down, these two observations again. So this is, yeah. So the good side or upside. I don't know. You get semi-perfect or perfect DC. No rebel, approximately no rebels. The downside, you lose some energy. Okay. That's okay, guys. Any questions so far?
We're good so far.
Okay. So let's, another application. This is maybe the last application for the diode that we're gonna explore. There are many applications. We didn't cover all of it, but we cover the most important ones, which is what's called diode level shifters. Okay, or the clamper circuits. I don't know why they call it clamper, by the way. Okay, maybe because my English is not my native language, but if you get, guys, any idea why they call it so after we explain it, then let me know. But anyways, so what is this level shift? As the name suggests, it will level up or down some AC. So basically, let's go what is required exactly, and let's see how to do that using a diode. So what is required is something like this. If you have an AC, so what is required? If you have an AC like this, just a sine wave, very bad sine wave like this one. Okay, so let's call it Vn. We wanna this, and this is T, and this is 0, Vmax minus Vmax. You want it to be like this. This is the same T. So for example, we wanna level it up by Vmax, by this amount. We wanna level up or shift up by, oops, Vmax. So what's gonna happen if we gonna let's see, okay. So it's like our time axis is leveled up, so we'll get the same signal. But leveled up. So this is 2 Vmax and this is 0. This is much better now. Okay. And by a paper, and this is easy to do, by the way. So if you have a source like this, you can do that very easily. Just put a battery in series. With V input. So this will give us this guy. But a battery by default is costly. I mean, you will pay some cost. At the same time, very bulky. So something like this. This is 1.5 volt. Assume that you want Vmax is 30 volt, then you will have bulkier than this, even bulkier. So this is you know, if we compare it to a diode or a capacitor in a circuit, this is very bulky, or even a transformer, it's comparable. Now, if you have even want a more voltage out of this battery, you will need, you know, you know, a bigger size, more bulkier one, or a bulkier one. So can we do that without using a battery? The battery is a very valid solution. If your you know, size limitations you know, are low, and you can, you know, increase, you know, the size of your circuit, use a battery, that's fine. But actually we can do that using a diode and a capacitor, and we can do that as a positive shift or negative shift. So let's explore first the negative shift. It's not a positive shift, but this is a circuit that you actually know. So let's see what is basically this circuit. So negative clampers, or negative clamper circuit. This is actually a negative clamper circuit. Which we know before, right? This is basically, if you remember, guys, this is a half wave rectifier with no load. So if we take the output like this is the half wave rectifier. But if we look at the output on the diode, it will be, so this is half wave. This will be okay. This is the half wave output. If we take the output of the diode, it will be the negative clamper, as we will see. So we're gonna draw it in that way. It is the same. It's a series. So I will just put the capacitor up, and because we usually like to have the output parallel to the input, we can say. So here is VO, which is actually equal to VD. And this is Mr. VC. Okay, so let's see how to analyze this circuit. So let's draw here the input voltage. Okay, so this is just a revision, as we will see now, just a revision for the first circuit that we took maybe two lectures away, on Tuesday, when we studied the half wave rectifier with a smoothing capacitor without no load. So basically at t equal to 0, a capacitor, we will assume the capacitor has no charge. Q is equal to 0. So VC is equal to 0, which is VO. I'm sorry, this is not VO now. VO is VD. Okay. Good. So here VC at t equal to 0 has a 0 voltage. And the diode will take all the input. So when the input start to increase, okay, the diode will be in forward bias, but it needs 0.7 to turn on. So as long as Vn is less than 0.7, diode is off. So no current will flow in the circuit. And if you have no current flowing, the capacitor will not charge or discharge. So no charging, no capacitor charging or discharging, because basically it doesn't have a Q or charges to discharge them, basically. When the input reaches 0.7 and beyond that, the diode will be on. So ID is larger than or equal to 0. So the capacitor will charge, and its voltage, which is VC, will start to increase. So since the diode is on, VD is equal to 0.7, and from Kirchhoff, VC is equal to Vn minus 0.7. One important note here, this is until will continue until t equal to t over 4. So let's draw this until t equal to t over 4. This is t equal to t over 4. Let's draw VC with before that at t equal to 0, and when V input is less than, let's do that. When V input is less than 0.7, we said that there is no charging, discharging, so VC is equal to 0, and if we apply Kirchhoff, VD is equal to, or V output is equal to V input. So assume this is the 0.7. So VC will be 0 here, and VD is equal to V input just V input, so it will be something like this. Yeah. Okay. Then when V input is larger than or greater than 0.7, VD is constant equal to 0.7. So until this point here, VD is constant equal to 0.7. And VC will be equal to V input minus 0.7. So it will just charge like this until this point, until the maximum point, just following the input until it reaches Vmax minus 0.7. We didn't do anything new. This is what we have studied 2 lectures ago on Tuesday. But at that time, we didn't draw or sketch VD. Now, let's see what's going to happen after t over 4. Let's do it another color. So after t over 4. When t larger than or equal to t over 4. We said that we have 3 options. So basically, when the diode when the capacitor was charging, the current was flowing in that way. So this was the positive and this was the negative. After t over 4, the input is decreasing. Then so now the capacitor cannot charge. The capacitor has 3 options. It charge again. This is not happen because the source has input less than the capacitor voltage. The second probability is that the capacitor will discharge, but this is also not valid because if it wanna discharge, it will discharge in that way, which is wrong because the diode cannot permit current flowing from N to B. So we said at that time that the only valid option is that the capacitor will continue with its voltage with no discharging or discharging, constant voltage. So basically, the capacitor voltage will continue like this, constant, equal to Vmax minus 0.7. This is what we taken. Okay. Now, so let's write this down here. So the capacitor will not charge or discharge. Okay, so review lecture 14 on Tuesday. So VC will be constant, equal to Vmax minus 1. The last voltage it reaches before at t equal to T over 4. Now let's apply this on the circuit, in the circuit. So we have here Vmax minus 0.7. We have here V input, and we have here VO or VD. So basically, if we apply Kirchhoff easily, VD, which is VO, is equal to Vn minus Vmax minus 0.7. So after T over 4, pick any point on V input, subtract Vmax minus 0.7, you will get VD or V output. So let's do that. Let's pick some important points. So let's take, for example, this point here. Let's pick this point. Let's pick, for example, something like V maximum over 2. Okay, let's see what's going to happen. So for Vmax, when V input equal to Vmax over 2, this point. So V out equal to Vmax. Oh, yes, Vmax over 2 minus Vmax minus 0.7. So Vmax over 2 minus Vmax plus 0.7. So this will be Vmax minus Vmax over 2 plus 0.7. Okay, this is 1 point. What's happening if V input is equal to 0? This is number 1. Number 2, when V input is equal to 0, VO is equal to 0 minus Vmax plus 0.7. Good. If V input is equal to minus Vmax, so VO is equal to minus Vmax plus 0.7. So this is equal to minus 2 Vmax plus 0.7. And what's happening if, let's take another point, this point at Vmax, the first point actually in the curve. So let's do it here. Number 4, V input equal to Vmax. So VO is equal to Vmax minus Vmax plus 0.7. This guy will go with this guy. So VO is equal to 0.7, which is that point actually. Okay. So basically, we will take that part here, that signal, and we will move it down by a shift equal to Vmax minus 0.7. So we're gonna draw the same. I will draw now this exact same shape here or plot here, signal here, exactly the same, but leveled down by Vmax minus 0.7. So it will be something like this. So let's take the important points, not to, So this is actually exactly the same as this. I know my drawing is horrible, but I'm telling you now, this is exactly the same as this. So this point become 0.7 as we proved. Look, when V input is equal to Vmax, VO is equal to 0.7. This is what we have, 0.7. And when V input is equal to 0, VO should be equal to V minus, oh, I forgot. Yeah, minus Vmax plus 0.7. So this here is minus Vmax plus 0.7. Then we have this exact negative half cycle, exactly the same with no change. It is just leveled down, as we said. So this part here is exactly this one. I know they are not, the sketch is bad, but they should be exactly the same, okay? And this point here is when V input is equal to minus Vmax, this is minus Vmax. We know that it will be minus 2 Vmax plus 0.7. So this point is minus 2 Vmax plus 0.7. And this is again minus Vmax plus 0.7. Then we will take this part, and draw it again here. So let's try to make it perfect. So this part is actually this part. And, we'll continue. And this is basically 0.7. Because at V input equal to Vmax, the output will be Vmax minus Vmax plus 0.7 equal to 0.7, plus 0.7, which is this point. Okay? So again, if we just ignored Vmax, okay? Compared to, if we ignored the 0.7 compared to Vmax. So you will not notice such, small positive shift. And your signal will not just be, down by minus Vmax. So as I said, we level shifted this signal here, this input signal, down by minus Vmax plus 0.7. If we ignore the plus Vmax compared to minus if we ignore the plus 0.7 compared to the minus Vmax, then we level shifted this signal by minus Vmax, just as our requirement for which is adding some level shift to the input signal. Okay. Now let's, before going forward, to convince you more, I will draw now, okay, but the analysis is yours. I will draw now the output if we assume the diode is ideal. If the diode is ideal, so there is no 0.7, okay? So the output would be something like this. So let's have another color. If the diode is ideal, you will have 0 here. Then just track this. So this is basically exactly equal to this. Then we track again. This is minus 2 Vmax. This is 0. And this is basically it's really bad. I'm very sorry. So, okay. You guys got the idea. My sketch is bad, you know. So this is minus 2 Vmax. This is minus Vmax. Okay. And this is 0. So with the ideal model, you know, you can see that the level is really minus Vmax. You guys get the idea, or still something not clear here? It is exactly the half-wave rectifier with smoothing filter, no load, but we take the output on the diode, not on the capacitor. That's it. Clear? So let's, you know, make this. If you just, you know, more analysis for you. So, I mean, you know, my drawing is bad, but this level here is Vmax, and this is also Vmax, because it should be, of course, symmetrical, but my drawing is bad. So it is the same exactly input sine wave, but instead of drawing it around the level, the axis 0, we are drawing it around the axis of minus Vmax. So look, sine wave, but around minus Vmax, not 0. Okay, so our final part on that chapter, or okay, on the diodes in general. Any questions so far, guys, before going to this new topic? Any question? Okay. So the final part, or something that I want to talk about, is the light emitting diodes, or LEDs. Okay, it's a special type of diode. It's not silicon. Okay, it's made of gallium arsenide. There are many, you know, many materials that we can use to make, but basically the same concept. The concept is it's a diode, it's still a diode, but this diode, when it's forward bias, it emits light. Okay, anyone, you know diodes, know LEDs before, or have an idea about them?
They're everywhere.
Yes, of course. Yeah. So it's just a diode, but when it's forward bias, it just emits light. That's it. That's it. Okay. Of course, there are some differences. I will give you some idea how we can get light from a semiconductor. Okay, but it's not. This is not the explanation for how it works. Okay. I will draw now the energy band diagram, but not for this diode. I will draw energy band diagram for some materials that can emit light. Okay, I will show you how now. So if you remember, guys, the energy band diagram, we have the valence band, we have the energy gap, which has no orbitals, so that you cannot find electrons there. Then we have the conduction band, and we said that, you know, for order to conduct, you know, electrons move from the valence band to the conduction band, and they leave behind a hole like this, and that's it. Okay. Now, any electrons that goes to the conduction band has something called lifetime. So it lives there for some time and get back. So this is an average time for the life of the electron in the conduction band. So after this, average time, it will go back to the valence band. Remember, guys, this is energy, or is there, the electrons go from orbital to another orbital. So it was here in some orbital, then it goes here to another orbital. And since we are increasing in energy in that direction, so this orbital has more energy than this orbital. Now to make the electron to move from low orbital to a higher orbital, we give the electron energy equal to the difference in the two energy levels. But what happens if the electron goes back to its lower energy level orbital? So it moves from a high energy state to a lower energy state. When the electron moves to that lower energy state, it will have lower energy. So that means some of the energy just disappeared. It's not disappeared, actually. It converts to another another form of energy, which is electromagnetic form, wave, just like wireless, okay, or light, electromagnetic wave. So when the electron goes back, it emits some energy. This energy equal to Eg, actually, approximately equal to Eg. Okay. And guys, Max Planck has relates the energy to the wavelengths of electromagnetic waves. It's equal to some constant called Max Planck constant, H, multiplied by the frequency of the electromagnetic wave. Okay, so I'm just giving you a highlight. That's not even a diode. It's just a single material. Diode is two materials, N type and B type. Okay, so if the frequency is within the visible range, then we will see light out of this process. So if you have a material like phosphorus, for example, guys, this is monitors that that you can see the heart rate or the CROs. Okay, the old CROs actually made of, these screens are monitors are made of phosphorus, and when it hits by an electron, so this electron for some time goes to high energy state, then when it goes back, the phosphorus will emit some light, so we can see the signal. Okay, that's some equivalent principle here. But this frequency should be in the visible range between red and ultraviolet. So if this frequency lies in the visible range of light, then we can see light. This visible range is between red and violet. Okay, that's a very highlight of what's happening inside the light emitting diodes. So light emitting is just a normal diodes. Okay, so this is the principle of operation, we can say. Some characteristics. And this is actually the symbol for LEDs, just like the regular symbol that we use for diode, but we draw two arrows out of that diode to say that it emits light. First of all, their VBI, the built-in voltage, is usually larger than 1. Okay, and that's basically depend on the type of material that you are using and also the doping. But it's usually larger than 1. So if I give you an example with a diode, with a LED, I will give you, don't assume it's 0.7. No. I will give you its VBI. For example, it might be, for example, 1.5 or 1.7 or 1.3, something larger than 1. But I will give you that number in the exam. Okay? So this is number 1. Number 2, the light will be visible since we use these lids to see some light. So light will be an indication for us. So we need that light to be strong. Okay, so it can be probably it can be probably visible to you. So it usually have some I forward minimum or minimum amount of current to give you a proper operation or a proper light for you. So it needs a minimum amount of current in order to emit a proper or more visible, we can say, light. Okay. Other than this, the the analysis, the characteristics, just similar to or close to the or exactly as the normal diodes. Okay. One particular application for the LEDs are 7-segment display. So let's have a very big division like this. So one big application is the 7-segment display. So basically for this 7-segment display, it is this one. If you, I know that you know it. It sometimes it's used in digital watches. I will draw it, but again my drawing is bad, but you will get that. No, I will just do it in a very simple way. So this 7-segment display is actually the display that we use everywhere. Okay. So let's name them A, B, C, D, E, F, G, H. Okay. Every one of those is actually, every segment we can say is just a circuit that has a LED and a resistor. Okay, so every segment here, or each segment, is something like this.
Are E and H the same segment? It would just be E, wouldn't it?
Oh, I'm sorry.
There's a decimal point on those displays. That's what that 8 would be.
Yes. So yeah, that's right. Some displays has, this is a very detailed, but I'm just giving you the highlights, so they didn't mention this. But some displays has a another LED, but it's a circle, not a circular LED. So you have the LED and you put a kind of something that permits the light in some specific area and prevent it from other areas. So you will see it like a segment. Okay. But anyways, so some other this segment, it's actually 8 segment, because you have a 7 segment for the number, it's the digit, we can say 1, 2, 3, 4, and sometimes you have also another LED for the decimal point. So you can have something like that 9.8, for example. So you have a 7 segment which will show the 8, another 7 segment which will show the 9, another segment which will show the 8, and another segment to show the decimal point. Okay, But I will just give you the basic principle. If you have 7 segment, which is just 7, no decimal point. Okay. But if you have, it will be another lead. So each segment basically either the lead, either the decimal point, or from A to what here, to G. Okay, it's just a circuit like this. So you have a battery, resistor, and your great lead. Okay, just something like this. Some battery here, let's call it VN, whatever. Okay, so for example, if you want to see, let's say 0, let's draw it, 4-digit 0. Then you will light all of them actually, except G. So here you will light something like this. A, B, C, D, E, F, except G. So all segments will be on except segment G. Okay, I think this is clear, right? You just need to choose a proper value for R, such that the minimum current that will flow in that circuit is larger than I forward minimum, which will be given for you. Okay, in the data sheet, or if it's an exam, I will also give you. If I ask it to choose a proper value for R, I will give you what's the required minimum current, forward current in the lead when it's forward. When it's reverse, it's just like acting just like the normal diodes. You know, reverse off I is equal to 0, and that's it. Okay. So that's basically, guys, 7 segment display. Any question on that?